Okay, so it's my pleasure to introduce Kamal Choudhary, who worked at NIST and now at Johns Hopkins, who spent a lot of time developing the infra ecosystem for the machine learning and spectral imaging data. So he started 5 years ago, right?
At NIST, it was around 10 years ago.
Okay. So time flies. But basically, when Kamal started to work on it, nobody thought that this type of things can be deployed on the instruments real time. Now they can. So that came with the vision and perception and vision and persistence. So it's great to have him here to introduce the AtomGPT and how machine learning models can be run on the microscopes in real time. The floor is yours, Kamal.
Thank you, Sergey, for the introduction and all the organizers for inviting me. Let me try to share my screen. Can somebody confirm if you can see my screen or not?
Yes, we can see your screen.
Great.
And we can hear you, which is actually very good.
Excellent. So that's great to hear. So hi, everyone. Good afternoon. As Sergey introduced, my name is Kamal Choudhary. I'm an assistant professor at the Johns Hopkins University. I have 3 affiliations, so Material Science and Engineering, Electrical and Computer Engineering, and Data Science and AI Institute. I also hold a position at NIST, National Institute of Standards and Technology in Maryland, and I was a staff scientist there for past 10 years before joining Hopkins. Today, I'm very excited to talk about atomgpt.org, in short, how to build a ChatGPT for material science. This is the outline from my talk. I'm pretty sure you have heard a lot about Agentic AI, but I'll give a very brief overview of my perception of Agentic AI. Then I'll talk about something called ChatGPT Material Explorer, atomgpt.org, and how to do benchmark for Agentic AI and so on. So let's start with the first topic. And I believe we have about 40 minutes, so 40 or 50 minutes. So number one is overview of Agentic AI. So before we go there, I would like to briefly point out the landscape of AI for material science. First, we have to appreciate computers do not know material science, physics, or chemistry. The only thing they understand is numbers. So how we can convert those sophisticated information of physics, chemistry, biology, or whatever domains of expertise it is, in form of numbers is our job as scientists. Now, when we say AI is an umbrella term, the idea is to mimic some sort of brain function. When you have data on the order of 500, we are talking about machine learning. When you have data more than 1,000 or so on, deep learning. Generative AI create contents like image, text, very famous nowadays. Agentic AI is takes action, it not just create content. If you want to know more about these application of deep learning methods in material science, we wrote a review article which is still relevant, quite up to date in terms of its GitHub, is recent advances in application of deep learning methods in material science. This was published about 4 years ago, but you can see it has been cited about 1,000 times. The idea of agentic AI is clear, and especially coming up from this industry, that we need to invest in agentic AI. If you look into this couple of write-ups from Google or OpenAI, it gives you a lot of information how to build agents from scratch. Also coming from NVIDIA CEO. So why do you need agentic AI? First of all, material discovery is very slow, expensive, and fragmented. This traditional AI can predict properties, but do not act or do not take action on your behalf. Most of these AI models that are trained on general purpose data, such as ChatGPT, Claude, are trained on data which are available on internet, but material science data itself is so huge that it can hallucinate. It can also create psychophancy, so it can be overpraise you about your outputs. Most of the models of agentic AI use, any AI agent you use, is based on Claude or ChatGPT or Gemini, which are commercial models, not open access models. The outputs of these commercial models can be non-reproducible. So if you ask the question right now, a second from now, you might have completely different response, which is not good for science. We want reproducible output in science. And as I said, these are not trained on this domain-specific data. So how can we solve this problem? There are at least two ways. Number one, if you consider this AI as a child, the way to teach a child is either teach them or train them. When I say teach them, you connect these LLMs or large language model or foundational AI models with specific scientific database and resources using functions such as retrieval augmented generation, RAG, tool calling, model context protocol, and so on. I'm sure you have heard about this term. Or you can take the foundational model and fine tune it using LoRa and PEFT, parameter efficient fine tuning methods. So these are at least two ways you can either use individually or combine this approach to solve these above problems that I mentioned for material science. I would also like to highlight the difference between predictive AI, generative AI, and agentic AI. As I said, predictive AI can give you input to output relationship, such as band gap prediction, formation energy prediction, and there have been several atomistic-based models like CGCNN, Align, and many others which can do that. It can also be used to do something like variation autoencoder, diffusion model. These are all predictive model. Generative model, well, diffusion model can fall in generative model as well. Generative AI model can produce text, image, and data. These waits for prompts, these are pattern-based responses. Agentic AI, you can consider as a brain, the AI, plus the hands, which can takes autonomous action. These are usually goal-directed, and it solves the problem using tools and planning. It can call APIs, search databases, run calculation, or run experiments. I usually introduce my students agentic AI using this strawberry test. If you go to atomgpt.org and ask a very simple question, how many R are there in strawberry? Okay. If I go to AtomGPT and select GPT OSS, the Meta Maverick model, and Google's Gemma model, and ask a very simple question, as I said, how many are in strawberry? You'll see that in some cases, we are getting 3. One of the Llama model give you 2, and the Gemma model give you 3. Now, these models, again, I don't want to judge any model, but what I want to point out, you always have to test the model for your specific task. Even for very simple tasks, they can hallucinate with high confidence. And also, this is based on how tokenization work in AI models. So always benchmark. So how can we solve this problem using agentic AI for Strawberry? Suppose we wrote a very simple Python code, count R. So this Python code gives you s.count R. If you have a string, it will count the number of R. And no matter what AI model you use, it will always be 3. So what we can do is we can take this general purpose model like LLM, like Gemma or Meta or GPT OSS, and connect it using this Python 3-line of Python code, which is hosted on AWS or other cloud provider or your own server, and connect it using agentic approaches. Now, anytime you ask the question, how many are in Strawberry, no matter which model you use, the model will first consult this specific 3-line code, then give you a response. So in this way, this model output will always be reproducible, always be correct. And this is one way to reduce hallucination using agentic AI. Now, let me talk about why agentic AI for material science is so hard. Why making that strawberry R example is so difficult for material science. First of all, in material science, we are dealing with heterogeneous data like DFT, density functional theory, if you are familiar with molecular dynamics, different types of experiments. Combinatorial challenge, you might have heard millions of times probably that if you consider periodic table, it has more than 100 elements. Even if you take a combination of 10, the number of combinations is 10 to the power 100 or more. Just generating the data set itself is nearly impossible, let alone training an AI model on it, like ChatGPT model on it. So it's very difficult. Number 3, the number of papers that are published in material science or in general physics or chemistry are mostly non-reproducible. If you read this paper on 1500 scientists lived on reproducibility in Nature by Monia Baker, you'll find that more than 0.5% to max 30% papers are reproducible. More than 70% papers are non-reproducible. At least it depends on the field, of course. So if your model, if your experiments is not reproducible, if you make an AI model on those, of course, garbage in, garbage out. Also, most of these material science experiments or computation are long running. So we need faster tools using surrogate AI model or other type of AI model. Also, if you want to solve this problem using agentic AI, usually those come with API cost, which may look very small, but as you build upon it, they add up. And especially nowadays when API costs are very high, this may really be pain in the neck. So multi-scale modeling, multi-scale experiment, combinatorial challenge, reproducibility challenge, these are some of the major ones. There are many other challenges. This is why I think building a ChatGPT or material science is probably the most hardest problem in the world right now. This is the most hardest problem. Even in the movies, like this is a clip from the movie Iron Man, where he's trying to make an arc reactor. He goes to the periodic table, does this fundamental principle of material science, processing, structure, property, performance, and then test its performance, and then evaluate it. Even at a movie scale, you can imagine it's so difficult. Think about how difficult it is in the reality. Luckily, from the US government itself, there have been initiatives such as Material Genome Initiative, $400 million investment, US CHIPS Act, former President Biden for $52 billion investment, and now Genesis Mission are trying to accelerate this task and solve this bottleneck. One of the infrastructure that came out of those projects is JARVIS, which we started in 2016, 2017, available at jarvis.nist.gov. Most of these applications are now moved to atomgpt.org in 2025. The idea is to use density functional theory, machine learning, force field, and so on to design and optimize the materials. What does it contain? We focus on quality of the data than quantity. We have about 100,000 materials. We have better functionals in DFT. We have properties such as elastic tensor, piezoelectric tensor, superconducting transition temperature, Raman spectra, STM images, defects interface, and so on, things that matter. Luckily, we have seen about 200,000 users worldwide and still growing. 2 million data download on Fixture, 2.4 million is the highest Fixture download in any branch of science. About 7,000 citations for the project, and these are some of the other 50 plus articles published. Now, once we have this data set, what we can do is connect with some sort of AI model. Here we will use ChatGPT to make ChatGPT Material Explorer. So building the high fidelity data set was an important part. So luckily in 2023 November, the CEO of OpenAI introduced a very interesting concept called GPTs, custom GPTs, where you can take ChatGPT and customize for your own task. So if you go to ChatGPT today, and on your left-hand side, you'll see something called Explore GPTs. And there you can make your own GPT. I made a Material Explorer 1.0 where you give your name, description, instruction, and some of the tools that you want to use, some of the app you want to use, and it will be customized for your task. So now, when you ask the question, for instance, how many materials are there aluminum oxide in Jarvis DFT dataset, it will first talk to Jarvis and then give you the response. Okay. So in this way, we can reduce hallucination because it's talking to a bona fide or a trustable source, not just database search, but also graph, neural network prediction, archive search for hallucination reduction, and so on. This was built about 2024. So this was published in the journal. We compared this with ChemCrawl, GPT-4o, and of course this model where this agentic model was much more accurate. It made a lot of news. GHU Hub made a big news article about this. A lot of people made a YouTube video about this. So it went viral. I'm not the only one doing agentic AI for materials. These are some of the other efforts that are going on. This is from, I think, Carnegie Mellon, ChemCrawl, Elegante from University of Toronto. This is from MIT. This is from Berkeley, China, university, I forgot the name. And of course, this AtomGPT API and ChatGPT Material Explorer. So now we talked about ChatGPT Material Explorer, which connects ChatGPT with Jarvis. But the problem is ChatGPT is a proprietary model. So how can we solve this? This was the motivation of making atomgpt.org. If you go to the atomgpt.org, it looks like this, where you can sign in with your email or your Gmail account or GitHub account. What do you get out of this? It provides open source models. These are models which weights known. You can also connect proprietary models if you like. And most importantly, it contains domain-specific, material science-specific apps. Remember the count R? strawberry test. It's like that. We have 50 plus such strawberry kind of app, more sophisticated apps, of course. It can search materials databases, predict properties, machine learning force field, protein structure analysis, X-ray, microscopy. Another important aspect, none of your data is stored. This is very important for scientists. That the infrastructure automatically deletes all the user data every month. Every first day of the month, it automatically self-deletes. It also allows function calling, tool calling, model context protocol with it. Currently, we have about 10,000 users already, and we have a YouTube channel for AtomGPT Lab, where you can see how several apps, 50 of these apps, and the agentic approach works. So in principle, as I said, AI agents have brain, the LLM, hands, and orchestration. So suppose you are studying a very detailed prompt, study the effect of nitrogen substitution in silicon carbide, fit the structure, visualize it, relax it, make an X-ray diffraction pattern, make an STM image, compute the band structure, run calculation. It's like a undergrad intern project. Now it's a prompt. So when you give this prompt, what will happen is we'll choose a model like GPT OSS, aka brain model. Then the brain model will talk to hands, corresponding hands, JARVIS DFT or Align or Microscopy GPT, AtomGPT, and then give you the response using this OpenAI agents or MCP-based methods. So these are how the principle of AGAPI works. Now let me show you some of the examples of these tools. So for example, if you're looking for a material like MOS2, you can search MOS2 and it will give you, for each of the material, you can go and take a look on the details of the structure, its phonon band structure, electron band structure, Raman spectra if available, infrared spectra, dielectric function, electric field gradient, elastic tensor, and many other properties. This was published in 2020, about 700 citations. Now, once you have these data sets, what you can do is make a graph neural network model. As I said previously, computers do not know physics, chemistry, materials. They only know numbers. So one of the ways to convert atomic structure to numbers is, suppose you consider this SiO4 tetrahedra. Silicon is the blue atom, red is the oxygen atom. One of the way to distinguish from silicon to oxygen is based on atomic number, atomic mass, and so on. These are node features. The H features are the atomic bonds, which are sort of a radial basis function based description. Now, this was fine until 2018, 2019, but they did not consider at that time bond angles. So this model called atomistic line graph neural network provided one of the first way to capture the bond angles using line graph. And in this way, we can capture angles, dihedrals, and so on. So now we took the JARVIS DFT dataset, trained models on it. And now if you go to the app and give it atomic structure, this is atomic structure with the lattice parameter, 3x3 matrix, the element type, and 3 XYZ coordinates. In just few seconds, it can predict your properties such as formation energy, mechanical properties, topological properties, magnetic properties, interface properties, and so on. This paper is cited about 800 times. Now we can also run molecular dynamics with it. So not just static properties, but also run molecular dynamics with it. So if you have atomic structure, which we don't know the lattice parameter, we just give randomly 5, and then for silicon, and then you can run optimization with this, and it will give you the optimum lattice parameters such as 5.43 or 5.47. Yeah, 5.46 or 47. Not just that, you can run molecular dynamics with it for atomic structure. Like if you have a system and you want to predict what will happen after a certain number of time steps, you can make some cool movies with this and see what's the mechanism of certain phenomena. Another important aspect is predicting phonon properties or dynamical properties. If you have atomic structure, run a phonon band structure, in just few seconds, it will predict the phonon band structure. So these are some of the applications of the force field part. Now, this is great, but Align model did not consider electronic orbitals, which are important for predicting band structure. This is where we propose this idea called SLACONET, Slater-Coaster Tight Binding Neural Network, where you take an atomic structure, and instead of representing atomic structure with bonds and angles, you represent it with the SPDF orbitals, S, P, X, P, Y, P, Z, and so on. Now, for each atoms for a corresponding bond distance, you get a Hamiltonian matrix. Those Hamiltonian matrices for each K point diagonalized give you band structure. Now, similarly, if you have atomic structure, this magnesium boride, if you run this on SlackOnet app, it will give you band structure, Fermi surfaces. So these are band structure which you can get atom projected density of states, orbital projected density of states. You can get fancy 3D visualization of your band structure if you like, which is important for something like ARPS kind of data. You can get Fermi surfaces, which are important for metals, and so on. All from a click. You don't have to know any coding. You don't have to know VAST, quantum espresso, and so on. And it's only limited. It cannot do lanthanides and actinides right now, which we are working on. But any other combination of periodic table elements you can simulate with this. One of my favorite classes of material is superconductors. So we made a superconductor database out of this, JARVIS, and characterized the electron-phonon coupling. And this can also be available at atomgpt.org/supercon to visualize something like Elias-Hoare function, omega log, and so on. Now, these are all theory. How about experiments? This is where it becomes more interesting. So we took the JARVIS DFT dataset and made a powder X-ray diffraction pattern with this 20 line of code. You can simulate powder X-ray diffraction quite easily. We took this data set for all the 80,000 materials and generate a model called Diffract GPT, where the idea is if you have an X-ray diffraction pattern, a chemist will describe the X-ray diffraction as the following. I see a peak at 20 degree with this intensity. I see a peak at 30 degree at this intensity, and so on. So you convert a spectra into text in a language, how a chemist will describe. That's your X or input. Your output is your CIF file, like atomic structure file, which is also a text. Now you can do text-to-text mapping, and it can generalize pretty well, which we are showing here with Diffract GPT with gradient boosting regression, which can, of course, predict only the lattice parameter, not the coordinates. But the Diffract GPT can predict you both lattice parameter and atomic coordinates. We found this one with full chemical formula in the input gives you highest accuracy or lowest error. And we can further refine with align FF or any other force field model. And we tested it for silicon, lab 6, hafnium carbide experimental data. These are tested experimental data. We also found, very interestingly, that even though the model was trained on perfect data, it can generalize reasonably well for defect data, where we can displace an atom and see how the diffraction pattern change, and which is interesting. Now, once we have this Diffract GPT model, we hosted it on Hugging Face. And in just 1 month, it got about 240,000 downloads. Just to put in perspective, this is more downloads for a month than DeepSeek model, version 3 model, which showed you that even a material science-based model can be so popular, so interesting. Now the model is now hosted on the atomgpt.org/xrd, and you have a X-ray diffraction pattern, a chemical formula. It gives you the pattern-based, matching-based structure, Diffract GPT-based structure, and so on. So you have lattice parameters, coordinates, and suppose you have lab 6N, which the material does not exist. There will be no match. But if you run Diffract GPT model, as I'm showing you, it will generate your structure. That's the one interesting thing about GPT model. They never say, they always generate something. So these are a reasonable starting point, at least for your, and you can also run writable refinement like GSAS, BGMN, and so on with this model inbuilt in it, just if you have the diffractogram. Now, this is fine for diffraction. How about microscopy? And this is where it gets more interesting. In 2023, we made a paper called Atom Vision. And the idea was, can we generate a data set of STM and STEM using theoretical models? And we used the data set. At that time, there was no chat GPT was probably coming in. I was at least not familiar with this. So we did classification, segmentation, graph, and inverse design for the atomistic images. So one of the way to generate the images using the Rutherford experiment, where we say the image intensity is proportional to z square or atomic number square. But of course, instead of square, we put 1.7 because we have some loss. So we generated such data set for perfect materials using this Rutherford model. These for graphene, iron telluride, and so on. You can see 1.7. And we took this data set to train a GPT model. So this is called Microscopy GPT model. So suppose you have a image and if you have a caption. So GPT, the visual language model or VLM, which will try, if given an image, will try to generate atomic structure. So similar to the diffraction pattern where we have diffraction pattern and CIF file atomic structure, here we have image to atomic structure. And we found that even for the test data set which has not seen, it did reasonably accurate job, which was very promising. Now this model is hosted on atomgpt.org/microscopy, and I'll show you a demo where you can load, for instance, iron telluride STM image, which looks perfect, but and you can generate the atomic structure with it. The app also comes with segmentation model so if you have detect atoms dots, it will generate the atoms and you can download the coordinates. This is based on the Meta SAM3 model, but we are considering new model like Gemma and other models as well. These are 7 of the apps I showed you. There are 50 plus apps, and these 50 plus apps, what happens, it becomes the tools or hands for the agentic AI. Okay, so this is one way to have reproducible output and reduce hallucination for many different types of application in material science. This also comes with tooling documentation at AtomGPT lab, github.io AG API. And it also comes with Google Colab Notebook, which gives you a very nice demo how to set up this with your account ID and so on, free of cost. Now, once you have this tool plus LLM and you know how to orchestrate, now you can ask questions in natural language. Okay, so for instance, if you ask how many superconductors are there in JARVIS, it will take the LLM model, talk to the tool app, and then give you the response in natural text. This was, of course, based on this paper on designing high TC superconductors with BCS-inspired screening, DFT, and deep learning. But the data has been available as a tool, as an app, which is always available, which the LLM can always consult to or talk to. Not just one prompt, it can go from many prompts. As I said, for instance, you can go up to 10 prompts, like take the structure, make a supercell, substitute, do X-ray diffraction, do optimization of structure, do band structure, all using one prompt. It will actually run this, connect different tools, and give you the results. Another example is X-ray diffraction pattern. For each material, find me the X-ray diffraction pattern, powder X-ray diffraction pattern. Now, finally, I would like to point out it's very important to benchmark this kind of models. So this is what we did in the AGAPI agents, which was published, I think, last week, where we found that the model, the base model, the LLM model itself can be more accurate sometimes than the agentic AI approach, which is quite counterintuitive. Why? Because we tested only on known data set, known materials. If the material is already known in literature, like in books and papers, these LLM models will definitely provide you very good response. But if they are not known, then you must be using some sort of tool calling. And this is where the importance of apps and tools becomes very important. And we benchmark this, and these benchmarks are based on this platform, JARVIS Leaderboard, which I will not have time to talk in details, but it's a multi-institution effort to improve the reproducibility and enhance transparency of benchmarking in material science across various domains, not just AI, but electronic structure, experiment, quantum computation, and so on. We also organize hackathons. So we organized one last year called Agentic AI for Science Hackathon. It was attended by about 350 participants. This is also published in the Machine Learning Science and Technology last week, I believe. And there will be one coming up soon in September, I hope. So you can feel free to leverage that. I'm open to collaboration. These are some of the list of my collaborators. So if you have any questions, thoughts, feel free to reach out. These are some of the wonderful team members I have. Jay, Riz, Justin, Akshaya, Frank, these are all doing fantastic jobs. And if you want to know more about my group, this is my website. So finally, I would like to thank the organizers again for giving the opportunity to talk about atomgpt.org. Please feel free to check out. It's free of cost. No credit card needed. And if you want to know more about this architecture or what's the importance, this is published in the Journal of Physical Chemistry Letters called AGAPI Agents, an open access agentic AI platform for accelerated material design on atomgpt.org. This is my email if you want to reach out. I also have a YouTube channel where I provide several contents on apps and demos and my talks. You can feel free to check that out. Also available on LinkedIn if you want to connect. We have an AtomGPT Lab Spotify channel where we convert papers to a podcast. And sometime I hear from my students it's much easier to listen to such podcasts than reading papers and so on, which is kind of state of the art, I hope. So with that, I would like to thank again for the opportunity to talk about atomgpt.org, and I'll be happy to answer any questions if you have. Thank you.
No, any questions?
There is a question.
Oh yeah, there is a question in the chat, Kamal. Can you see the chat?
Yes, I can access now. We commonly think that a projected STEM image is not enough to predict the full structure. I wonder how did the Microscopy GPT cover the Z information not embedded in the image? That's very interesting. So this was assumption that the GPT model can do it. And we found that, and this is why we did the test on 2D materials. I forgot to mention, we primarily tested Microscopy GPT on 2D material data set of JARVIS, not 3D. So for 2D, it did a reasonable job. And I believe it can be extended to 3D as well, like the full in Z depth. So it's still a proof of concept kind of idea.
No, any more questions?
So how much does hallucination of LLM affect the property prediction? So as I said, as we showed you in the benchmarking, if the model, if the question you're asking about is for a well-known material like aluminum oxide or magnesium boride and so on, the LLM model gives almost non-hallucinated result. Sometimes it's better than the tool calling itself because those tools are based on data sets such as DFT and so on, which have approximation. But the main player is when you ask about unknown materials or materials with defects, interfaces. There, you may not have trained data for the LLM, and there hallucination becomes critically important. And this is where we need agentic AI or tool calling based method.
I have a question. So regarding the database that we're using, for example, the one I'm seeing here, the materials. So is it something that you are like extracting from some database, or is this something that you have generated for this setup?
I'm not sure. I'm not sure they hear. Do you mind coming here to ask? Yeah, sorry about that. There are some minor issues with the sound streaming today, unfortunately. Yeah, please.
So I have a question regarding the database that you are using here for the Materials Explorer. For example, in the 2D materials, I see like there is a list of materials I see. So is it something that you have generated for this setup, or you are extracting from some database?
No, we have our own JARVIS 2D data set for about 1,200 materials that we published in 2017. It has interesting idea if you want to learn about how did we found those 2D materials is most of this DFT databases out there, they use a particular function called PBE, which really overestimate the lattice parameter of 2D materials, 2D bulk materials. So we did a trick where we found out how many materials are there where the lattice parameter error is more than a certain percentage. And then we found more than, I think, 6,000 or 5,000 materials like this. And then we manually made a single layer out of it. So we have single layer and the bulk material. We calculated the energy of them using DFT. And then we calculate something called exfoliation energy, which is the difference in energy of making the single layer from the bulk. And if it's less than 200 milli-electron volt, which is 200 milli-electron volt per atom, which is a van der Waals bonded energy, then we call 2D materials. So we have such 1,200 such materials, which we primarily use for Microscopy GPT.
And you are also working on adding more materials to it, so.
Not at the moment, but there are other data sets such as C2DB and Alexandria 2D data set. So some of my students have expanded Microscopy GPT on those data sets as well.
Okay, sure. Yeah. Thank you.
Sure. Golden question. Is there a JARVIS database for experimental data? I wish. So we are trying to make, so the powder extra diffraction pattern is one of them. We have some data set. But that's the extent of it right now. But we will try to collect it for some zeolites, like we have some zeolites adsorption isotherm from the NIST SRM data. It's all part of the JARVIS leaderboard, which is a different repository. And some STM images for some catalyst nanoparticles. So not thousands and 100,000s, maybe 10s, 20s, which we use primarily for benchmarking. Is there any documentation on benchmarking of simulation results from AtomGPT apps with traditional apps? Is there any documentation? Well, if you look into the AGAPI agents paper, it does not, well, in a way, it compares to DFT. So formation energy of this material is that, and the formation energy from LLM is that, formation energy of LLM plus tool is that. So you can compare like this, right? But it does not run on the fly vast quantum stochastic right now, but you can if you want to. So currently, if you want to know more about this benchmarking of the agents, I would refer you to that paper, AGAPI agents. In the bottom, I think figure 5 or 6, we do talk about how does the tool calling compare with non-tool calling or only LLM-based response.
Okay, seems no more questions. Thank you very much, Kamal, for your interesting talk.
Sure. Thank you for the opportunity. Bye.